videos on oxidation numbers.
So when we're talking about oxidation numbers, we have to pretend that all bonding is ionic. All bonding is not ionic, of course, but we have to pretend that it is. So oxidation numbers are a type of formal charge that we use to track which species gain and lose electrons over the course of a reaction. By formal charge, we mean a charge isn't necessarily exactly the charge that's on the atom or the ion in the compound. So our first rule is that for ionic compounds, the oxidation number will be equal to the charge on the atom. Since we're pretending all bonding is ionic, it should work well for the ionic compounds, and this is the best way to start with oxidation number. So here we have hydrogen chloride, oxygen gas, chlorine gas, magnesium iodide, elemental iron, neon, sodium oxide, and iron 3 oxide. And you can see that all of these oxidation numbers in red are in fact the ion charges on these compounds. Any atom in its naturally occurring uncombined form has an oxidation number equal to 0. That's the oxygen, chlorine, iron, neon, and so on that we see directly above. So there's a third rule with oxidation numbers, and we get this from the ionic compounds, again, that the sum of the oxidation numbers multiplied by the subscripts should be equal to the charge on the compound. So for instance, the iron 3 oxide from above, you can see that the 2 plus 3 charges and the 3 minus 2 charges here add up. And they add up to the total charge on the compound, which is 0. So the 2 plus 3s and the 3 minus 2s add up to 0, which is the charge on iron 3 oxide. We can explore this rule a little more by looking at the sulfate ion. So here we have the sulfate ion. It has a 2 minus overall charge. If we say oxygen is more electronegative than sulfur, it'll take its negative 2 charge and sulfur winds up as plus 6. Why is that? Again, oxygen is more electronegative than sulfur. Therefore, we consider oxygen in this make-believe all ionic scenario to have stolen sulfur's electrons. In other words, in that what we know to be covalent bond, the electrons are considered to be only attached to the oxygen and having been lost by the sulfur. Okay, this whole thing is supposed to have a negative 2 charge, so 4 minus 2s on the oxygen, and it turns out we need a plus 6 on the sulfur. You can see that all these guys add up and make the negative 2 charge. It's a great rule. It helps us to get the oxidation number for many atoms. So oxygen has really only 3 possible oxidation numbers, and in its uncombined diatomic form, we give it oxidation number of 0. In diphosphorus pentoxide and almost all other compounds, it would have an oxidation state of minus 2. Except in peroxides, like this one, hydrogen peroxide, or sodium peroxide, or any of the other peroxides, where we take an oxidation number of minus 1. Hydrogen, too, has its own rules. Uncombined, in its naturally occurring form, it would have oxidation number 0. In almost all other compounds, it's at plus 1, acting as the metal losing its 1 electron. Except in metal hydrides, like calcium hydride here, where hydrogen is acting as a nonmetal and gaining an electron from calcium. The last rule about oxidation number is really an extension of the sum of charges rule, and that is that polyatomic ions can be broken out of a compound if that's useful. So for instance, we can look here at ammonium chloride and calcium nitrate. Here we have ammonium chloride and calcium nitrate. If we break these two compounds apart into their ions that form them up, then we can see that we can get the oxidation numbers for ammonium as minus 3 and plus 1 here, and for nitrate as plus 5 and minus 2, on those rules separate to the calcium and the chloride. In sulfuric acid here, we can see the sulfate ion that we saw before and the 2 H pluses at plus 1. Here are a couple of general examples we can look at about oxidation number. Methane here, you get minus 4 and plus 1. Down here on carbon tetrachloride, you get plus 4 and minus 1. And on the acetic acid, it's worth looking a little bit more closely here. Turns out the 2 carbons have a minus 3 and a plus 3 oxidation number respectively. And that is because the 1 carbon on the right-hand side, you see it's attached to those very electronegative oxygens, is considered to have lost its electrons, whereas the carbon on the left is considered to have gained electrons from hydrogen. So, how and why to use oxidation numbers? Well, we like to know which compounds got oxidized and which ones got reduced. So here we have in this reaction with lead 4 oxide and iodine, making the lead 2 plus ion and iodate. Assigning all the oxidation numbers, we can see that iodine's oxidation number changed from 0 to plus 5, and therefore iodide was oxidized. It was oxidized by losing electrons. We can also see that lead's oxidation number was reduced from plus 4 to minus 2, and therefore lead was reduced by gaining electrons. Here we have manganese 4 oxide becoming manganese 3 oxide. And this is a so-called half reaction. We only see the manganese oxide being reduced here and not whatever it was being oxidized. We'll get into half reactions more next time. And here we have another one. This is chloric acid, HClO4. And the hydrogen, of course, doesn't change here, but the chlorine is seen to go from +7 down to -1. It has a change of -8. In other words, it was reduced by gaining electrons. This is another of these so-called half reactions. We'll use the half reactions quite a lot in our next lessons, so do stay tuned, everyone, for our next lesson on half reactions, where we'll use more of these oxidation numbers. Also, have a look at the next 2 videos in the playlist for more on this topic. And remember, next lesson, lesson number 26, redox half reactions.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.